All right, so welcome everyone. Thanks for coming here. My name is Ingo Grothus, and I'm giving the next talk on enterprise call analysis and generic call description. Now this is going to be more technical. It's mainly about how a system can be designed for enterprise call analysis with Asterisk and other call systems. Now, we've been working on this for about 1 year, and we'd like to share our experiences and findings with you. Right, but before I start, I would like to tell you a little bit about myself and the company I'm working for, so you know a little bit better who's talking to you. By my name, you might have already guessed that I might be Dutch or German, which is quite right. I'm from Germany, but very close to the border to the Netherlands. I'm 38 years old, and many of these years I spent with traveling, playing guitar, riding my motorbike, and doing lots of technical stuff with electronics and computers. So I started 30 years ago with programming a Commodore C64, maybe you remember. And by that time, it was already clear that I would go into that direction more professionally. So I graduated 2006 from Aachen University with a degree in electrical engineering and information technology. And 1 year later, I joined Ericsson, the Swedish telecommunications equipment company, and worked as a research engineer on the virtualization of communication systems and development of the new cloud product line. After resigning from Ericsson, I decided to intensify my traveling experiences, and I spent 8 months traveling from Southeast Asia over Australia, New Zealand, and Polynesia to South America. Now, since 2013, I'm working as IT engineer for telecommunication infrastructures at the LVM insurance company. The LVM is a well-established insurance company with over 3 million customers and a strong focus on the German market. We've got our headquarters in the city of Münster with about 3,600 employees. And we've got 2,300 remote offices across Germany with further 4,800 employees working on direct customer relations. Right, so let's start with a look at the big picture. Our goal is an enterprise-wide evaluation of communication processes. But how does our enterprise look like? So let's have a look at the map. First, we've got our headquarters located in the city of Münster, where the green point is. We're using 2 communication systems here, the Asterisk for office communication and CCOM for our call center. And second, we've got our remote offices across Germany, which are depicted by all those little gray dots. They're using the Datus entirely, which is also based on Asterisk. So we've got 3 independent communication systems here, and some calls have to be moved. For example, when the customer calls an agent in the remote office, and the agent has to ask an expert in the headquarters in order to answer the customer request. So in this case, it may as well lead to the situation where the agent is transferring the entire customer call to the expert in the headquarters. So the problem that we get here is that the 3 systems have got an isolated view on the call. Though the call is one business process, we may end up with 3 independent, incomplete, and disconnected descriptions, which are depicted by those colored puzzle pieces. So the goal of our project is to comprehensively evaluate those disconnected call paths. And to achieve this, we have developed a system called TPA, Telephone Process Analysis. And its main tasks are interpretation of the proprietary data, which means knowing the structure, semantic analysis, which means knowing the meaning, and generic remodeling, which means extracting interesting details and remodel them in a connectable way so they can be finally put together and we can piece the puzzle together. Up to now, we were focusing on developing the TPA for Asterisk office communication. So combining the remaining puzzle pieces is the next project step. So as you can imagine, this is a lot of work, and you may ask why all the effort? Now the answer is that phone calls are still the key medium for customer communication in our business. So calls are essential business processes for us. And important processes need permanent optimization and monitoring. So for instance, you could evaluate usage patterns from different perspectives. So from a customer perspective, you may ask, do they find the right way to the right agents quickly and easily? Or do they have to dial many extra numbers or wait in different queues? Or ask from the other side, from the agent side, are they able to answer the customer requests directly, or do they have to call back many colleagues to answer the customer request? You may also be interested in finding out what call features your employees mainly use. Maybe they don't know about useful ones, so a training might improve efficiency. And that is the actual goal of usage evaluation, to improve business workflows. We already use this for staff planning, because the demands on call center teams change depending on external events, like weather conditions or traffic accidents. And by looking at the real-time statistics, you may notice understaffed teams or overcapacities in other teams. And you may also want to have a look at workflows after organizational changes, because they might become inefficient without the right training. So in that case, you would observe that new teams with new responsibilities have to call back other teams, other colleagues to answer customer requests. And of course, it's also important to keep an eye on important processes from the technical side in order to identify bottlenecks or technical problems. Waiting queues may be too long or too short, which may indicate that there is some problem connecting agents or some queues being unreachable or unknown. And there might also be some configuration errors, like some people setting up call forwards, so in the end they form a loop. And they may also lead to wrong numbers. So there are many things you might want to keep an eye on from organizational and technical perspective. Right, so let's look at the technical specifications. We're using Asterisk version 11.6 with about 4,000 users, extensions, and 200 queues. Well, version 11.6 may seem a little bit outdated, but it's a well-established LTS version, and since migrations are an expensive thing for big companies, it usually takes a while to migrate to a new version. So in order to keep the load on these Asterisk servers as low as possible, we're using a multi-server setup with 4 well-equipped hardware servers. They've got a 12-core CPU with 18 gigabytes of RAM. And the normal business days, we get at peak times, we get a load of 200 concurrent calls, which is from 10 a.m. to 2 p.m. And this loads the CPU to up about 10%. So we don't have to worry about audio delays or the like. Now, while doing their jobs, these Asterisk servers generate a lot of data about calls, which we are actually interested in for analysis. Most of this data comes from the cell, the queue, and the CDR log files with an average rate of 40 events per second. That means in order to process calls in real time, the TPA server has to be able to process 40 events per second. This is working quite well with a virtual server with a 2-core CPU and 4 gigabytes of RAM, which is, by the way, the smallest machine available in our data center. And while processing the data, which also means exporting data to external applications on the users, the typical load of the CPU is about 25%. So we could even speed up the input rate to about 4 or 5 times real-time speed. Right, so now let's look at the design details. We see 5 processing stages. And because processing can be easiest described as application of models, I will show how the processing stages, the tasks, relate to the corresponding models. Okay, so at first we have the data collecting stage, which simply imports Asterisk raw data, sends it to the TPA server, and creates base objects that we call events. Now, these events are depicted by those gray bubbles on the top. And some of these events are irrelevant, like config reload events. And they will be removed by the sorting and filtering stage in order to speed up the further processing. Events also have relations and they are evaluated in this stage by being combined to a more abstract object that we call a process. So these two stages, they need knowledge about the structure, types, and relations of the base data, and that is what we call the base model. Now, most of the work is done in the next two stages. The semantic analysis uses semantic knowledge of the analysis model for abstraction. That means to combine related processes of different types and to extract interesting information. This information is then used by the generic remodeling stage to create a more abstract object, that is the meter object. The meter object is described by the generic model, and it contains all needed information for system-independent call evaluation. Finally, the customized export stage uses export models to transform the generic data into user-specific formats. And they are then exported to user applications, so they can then do the really fancy stuff with our call data. Right, so the next slide might look a little bit complicated, but we don't have to go into every single detail. It's mainly about where the processes run and how they communicate. So the big yellow boxes that are our machines, and the orange ellipses are the TPA processes running on those machines. So we start with the TPA agent in the upper left corner. This one simply keeps looking for new asterisk data and sends it to the TPA server over a TCP connection. Now, the data is sent to the TPA socket, which is the first process running on our TPA server. This one simply parses the input data and creates base objects, that is, these are the events objects, and stores them in a database. And as soon as an event group is complete, which is indicated by certain event types, it will create a related process object and send a notification message to the next process. Now that is the TPA analyzer, and it constantly analyzes new processes, which means it searches for related processes of other types, combines them, and extracts interesting information and stores that in a meter object. Now, whenever a meter object is created or changed, an update message is sent to all the registered TPA apps. And they may also run on external machines. That is why they are not in a yellow box. Right, so just one step is missing here because the apps, they need access to the database contents to get the object's details. Now that is where the TPA service process comes in. It provides a secured access to the database contents over HTTP or web service transport. And that is also the point where administrators may check the database contents with a web-based graphical user interface. And if we get enough time, we may have a look at that graphical user interface later. Right, so before we move on to the next slide, let's look where the models are located. The base data is created by the TPA socket using the base model. The TPA analyzer uses semantic knowledge of the analysis model for creation of meter objects. Meter objects are described by the generic model. And finally, the apps do the post-processing using export models. Okay, now let's look at the models themselves. But before I start with that, I would like to ask you about your experiences with Asterisk call logging data. So did anybody of you already had a look into cell or CDR log files? No? Not too many? Right, so some of you might already know about unique IDs and linked IDs, but for the others, don't be afraid, I won't go too deeply into the details. I will just emphasize the important aspects and give an idea on how the analysis works. So I'll start with one important modeling aspect, which is about IDs. Now, most of the work is about evaluating relations between objects. And if you get a data set without an ID, that's like getting a puzzle piece without knowing to which of 1,000 puzzles it belongs to. So it's pretty useless. We need IDs to connect the information from different sources, which can be different call systems, different network servers, or different data types. The Asterisk is offering two kinds of IDs. Unique ID, which is an ID for a channel, and linked ID, which is an ID for a group of channels, usually a complete call. Now the problem with these IDs is that unique ID and linked ID, they are only unique and valid in a local server scope, which means that every server is choosing its IDs independently. So quite often the same ID is assigned to different calls. Now this leads to a problem in multi-server setups, because calls, they are not only processed on one server, they can move. And on another server, a different ID may be used for the same call. So how do we connect those call paths? Now, we use a pragmatic solution for that by letting every SIP system, for instance, media gateways or the Asterisk itself, assign an enterprise-wide ID in the SIP header. It's a custom header field called XRConID, or short XID. And once created, this ID will be kept for the call on all SIP systems. And our Asterisk servers, they store the XID in our base data log files as user field, and it keeps its value across different servers. So this ID is mainly enabling cross-system call analysis. Right, so let's look at the base model and the base data. We got three different data sources: the CDR, the cell, and the queue log files. And the CDR log file gives us information about finished calls, like timestamp, source destination, call durations, call result, and some IDs. Now, while this is maybe the most important or interesting information, it's very basic and sparse, because the complete call description has to be reduced into very few CSV fields. So the analysis of complex scenarios is not possible. For instance, call forwards, call pickups, call transfers, and the like. Okay, next we get the cell, the channel event log. And this one contains continuous information about events happening in channels, which are micro elements for calls. And since usually many events occur per channel and many channels are used per call, this is very rich information. So instead of just one line per call, as for the CDR, we get about 10 to 100 CSV lines in the cell log file. But still some important information is missing there. For instance, the call result, which we get from the CDR field disposition. Finally, we've got the queue log file, which contains information about queues, agent, and calls. So for instance, which agent has answered a certain queue call, and what position the queue call had when entering the queue and when leaving the queue. So in order to get the full picture, we have to evaluate all the three data sources. That means we have to combine the data sets, and that is possible by looking at the IDs. The next slide shows an example for the analysis model. That is where we really look at the details and the meaning. But before we start, let's look at the linked ID to make sure we got everything. So the linked IDs show all the same value. They start with a chance start event, and they end with a linked ID end event. So we get a complete call here. Okay, let's look at the first line. It has a timestamp, an event type of chance start, initiated by Peter with a number 6086 and so on, to destination 3233. The remaining fields are about IDs. Okay, so let's write that down in an imaginary notepad, and let's look at the next line. This one shows that it's an app start event with an app name dial, and when we look at the app data field, we see a new number, 5779. So this line basically means that the channel is getting a new destination here, and this is actually a call forward. The next two chance start lines doesn't contain any new information, so we skip them. And the next line, the next app start line, shows that an application named Q is started with the ID with the number 5779. So the call is entering Q5779 at this point. The next chance start event says that the queue is basically trying to connect the call to agent Daisy. And 6 seconds later, we get an answer event on that channel. So that means that the call has now been connected to agent Daisy with number 5098. The next two answer events are basically about passing the answer to the other channels. So we can skip them. And the last really interesting events for us are the bridge start and bridge end events. They say that a bridge for an audio stream has been established, so both sides can talk to each other now. Now finally, let's look at the timestamps to calculate the call durations. The time between the first event at 10:30 and the last event at 10:35 is about 5 minutes. So the complete call lasted 299 seconds. The time between the first event and the first bridge start event is 6 seconds, and that is basically the time needed for call setup and finding agents. So let's simply call it ring time. And finally, the time between the bridge start and bridge end events is the time both sides spend talking. So this is talk time, and it's 293 seconds. So at this point, we do know quite a lot about the call. We do not only know source, destination, and times, we know the actions that took place during the call. And that can be very valuable information for further call evaluation. But before we do that, we have to store the information in a new data structure, which is described by the generic model. Now, the definition of this structure should be considered carefully, because it should contain all information that we need for further evaluation, and it should be flexible enough to also describe call scenarios that we maybe haven't thought about yet. And it also should be generic enough to be applicable to other call systems. Right, so let's look at the example. We've got a timestamp field, we've got a type field, source destination, a received number field, which actually shows the number that finally received the call. We've got call times, durations, result, then a list with details about the call, a list with involved queues, a list of actions that took place during the call, then the XID, which is our global identifier, list of systems that have been involved, and finally, the list of base processes that are related to this call. And here we can see how data is combined, because the list of actions that took place we get from the cell processes. That is what we have analyzed on the last slide. The call result we get from the CDR process. And the queue process gave us some extra information about the queue, like position when entering the queue and when leaving the queue. Now, all of these fields can be divided into two basic groups, elementary fields and optional fields. While the elementary are always there, like source destination, talk times, and so on, the optional ones depend on the actual call scenario. And it may happen that multiple values would apply for one field. For instance, if a call had 3 forwards and we just have one forward field, which one should go into the field? So that is why the data model should be extensible. You don't know how complex a call will get because it depends on the actual call scenario. And single fields may require lossy information reduction, and that is why we use extensible lists for such call attributes. And we use a document-based database that natively supports flexible data structures. The final point is about cross-system call identification, which I have mentioned before. If we want to comprehensively evaluate a call on different systems, we need a common ID to identify the call and to connect the information. This ID must be known on all systems, and it must be referenced in every call dataset. And as I said, we have implemented this as custom zip header, and that is working quite well so far. Okay, so finally we'd like to do something with our call data, and that is where the export models and applications come into play. For instance, we could export the call data as filtered or enhanced data to other statistical applications of our users, who may then use it for staff planning or workflow improvements and so on. We can also enhance the metadata by importing additional information from other databases, like organizational information, to know which teams or departments have been involved in the call. Or you could also import call categories to categorize the call into customer-related, internal, and involving remote offices and so on. Another application would be to send an email report with specific statistics every hour. And applications can also keep track of real-time conditions, visualize them, and notify the management in exceptional situations. Right, so at this point you might be saying that this may be working right now, but how do we handle changes? Now this is an important question because analysis of proprietary data is always sensitive to changes. And changes will occur. Let it be a major update of the base system, or some minor changes to a dial plan which affects how output is written to the log files. As soon as the models doesn't fit anymore, the analysis will get into trouble. That is why important maintenance and design aspects are to make the models easily adaptable, to add version information to input data, and to instantiate the right model based on the input data's version. Now, how did we reflect this in the implementation? First, we have implemented all models as classes written for a specific system version. Second, all input data comes with version information, so the right classes can be instantiated. And third, we're using class hierarchies to be able to easily extend and reuse old models and to abstract generic code into base classes. And that way, the adaptation effort mainly depends on the degree of changes in the input semantics themselves. And I should add that mainly the base model and the analysis model are affected by changes. Right, so what's the current status? We have developed, finished development of the first version. We've integrated that into our productive environment. Next month, we will start with productive use. And for sure, we will find need for improvements based on our practical experiences. And as soon as everything works well, we can integrate all the other systems to really make it an enterprise-wide evaluation system. So if all this sounded interesting to you, you might be happy to hear that we'd like to make TPA soon available as open source. We'll have to review the code first, so publication will probably take place in the beginning of next year. But the SourceForge project already exists, so if you'd like to discuss about TPA or give some feedback, feel very welcome to visit us on sourceforge.net, projects, telephone process analysis. Right, so that's about it. We've got 15 minutes left, so I'd suggest we start with your questions and see whether some time remains for a short demo. Thanks.
Any questions for Ingo? I'm sure there are.
Oh, not too many.
No questions? Oh, there we go.
Do you have a sample of one of the outputs?
Yes, sure.
Yeah, so we saw the basic data, but it might be nice to see how this is visualized.
Okay, then we go to the graphical user interface and have a look at the final data. Right. Okay, this is how it looks like. I'll quickly introduce the user interface and then show some final evaluated data. This is the query tab. So here we can start search requests. And we have a search form here with time and numbers. We can also not only search for phone numbers, we can also use team IDs or the like. We can search for certain agents or queues. We can search for certain attributes, call details, call actions. We have different customers that we can select or deselect here. We have different object types, event, process, meter, different data types, cell, CDR, queue. This is a validation feature. We can search for certain IDs, so unique IDs, linked IDs, or the hexagon ID. We can search for specific systems involved in the queue, in the call. And yes, so what we get there is the contents of the databases. So for instance, here at the top, we've got meter databases, then we get the process databases, event databases, and so on. So we can now start a search query for, let's say, 10:30 to 11:30. I hope I get a connection here. Right, so this is a list of calls that have taken place between 10:30 and 11:30 in our company. And we can see these meter fields here. So start time, source, destination, and so on. This is just a small selection of all available fields. There are many more, but they're not so interesting. Right, so for instance, we can see, let's have a look at the actions list here. Oh, this one looks interesting. It was started, I can make it bigger. Right, so now we get only this call. It started with a call to 3103. It has been forwarded to number 5751. That one was a queue, and finally the agent 2258 has answered the call. So we've got also the base events here, which are the cell events, or the CDR events. And every time such a meter object is created, as I said, a notification message is sent to all the registered apps. Which means if we get a user app, I'll quickly go to the apps tab. So we could register an arbitrary number of apps here. And once they get some meter information about the call, they can decide whether it is interesting to them or not, and whether they want to do a certain action. So maybe a pop-up on the screen, or having a bell ringing or whatever. And maybe at this point where I'm here, let's have a look at the app list. We've got an app called import Kogia config, which is what I just said, importing organizational information. So we've got teams and departments and so on configured here. Then we've got an export or two export apps, which basically take the input data and write them into other databases, which are doing some other fancy stuff with it, like displaying them on a screen or other things. We got an email notify app, which simply picks, well, every hour it picks a list of calls that have taken place and sends statistics about that to certain recipients. And we've got two validation apps which simply compare the results to other data, so to get an idea of whether this data was plausible. Right, so getting back. Yeah, this is actually the information that gets processed by the applications then. So whatever the applications then do, that is up to your mind and creativity. Right, so we've got another tab here. Maybe that could be interesting. This is a sort of real-time monitor. So we can see calls that are happening right now. Maybe my colleague Andreas can help me, with running a call. So Right, this is now the list of calls that have taken place in the last 60 seconds. Maybe Andreas was a little bit too fast. Well, so that is something you can do with it finally, to just have a time window of the last 10 seconds maybe to see what's actually going on the systems. And yeah, something's happening right now. Okay, so this is a user interface, and you can do quite a lot with that. It's up to you what you do with the applications. Are there any more questions?
Any questions for Ingo? It's fascinating stuff. No?
No more
No
questions?
questions? Okay.
Right.
Well, thank you so much, Ingo. Let's hear it for Ingo.
You're welcome. Thank you.